Good morning, students. Can you hear me?
Good morning, sir.
Morning, morning. Excuse me for the delay. Just installing some updates for my graphic tablet. So, a quick update on what we are planning to do today. So, last class, we had discussed the last segment of the fluids, and we did a bunch of questions as well, right? Did we complete capillary rise?
Yes, sir.
Okay. One second. So today's plan is in today's class we'll be uh, trying to you know uh, complete this the first at least the first lecture. Restart your system. I'll restart later. Okay, never mind. So today's class will be around the first chapter in the segment of thermodynamics. Thermodynamics in physics is divided into three segments. You'll have thermal properties, where we talk about specific heat, etc., etc. Uh, then we also talk about thermal expansions within the first chapter, that is thermal properties. We'll also talk about conduction of heat, etc., in the first chapter of thermodynamics. Then we move on to the next chapter, the second chapter in thermodynamics, which is regarding the usual that you have studied in chemistry, the zeroth law, the first law, and the second law of thermodynamics. And the last segment that we'll be doing in this is kinetic theory of gas. So the kinetic, that's the third chapter that falls under the thermodynamics topic, where you'll talk about the ideal gas law, where it came from, and what does that ideal nature mean, right? So those are the things that we want to discuss, okay, over the lecture series on thermo. After thermo is done, we'll have two chapters left: oscillations and waves, right? So this is one major segment of physics which is very high weightage, just because of the fact it comes in two subjects. So if you do thermodynamics properly, I think you get a lot of benefit out of it, because it's there in both chemistry as well as in physics, right? So the signs are a little bit different. Like somewhere it is positive, like in physics it's positive, in chemistry it's negative, the same quantity. So there's a small conventional difference between physics and chemistry, but overall concepts, the basic concepts regarding the thermodynamics will be same for both of us, both of the subjects, sorry. So without further ado, let us first start the first topic in thermodynamics, which is and the name of the chapter is thermal properties. Okay. And I'll start by talking about uh, what is the difference between these two words, right? Because we have been used to, these words a lot, but we don't seem to understand the difference between them. So, can someone tell me what is the difference between temperature, heat, and internal energy? What is the difference between them?
The
Anybody?
temperature just gives us the extent to which a body is hot or cold,
Mm-hmm.
whereas heat is a form of energy.
Okay. What about internal energy? And what's the difference between the three?
So internal energy is the energy that is associated with the system.
Okay. Hmm. Cool. Okay. I'll make this simple for you. Just answer me whether this statement that I'm saying is correct or not. If a body has higher temperature, can I say it has more heat?
Yes, sir.
Everybody agrees with this statement. And I'm being very specific here, and I'm very I know I'm sending out the statement in a very simple manner. If I say a body has more temperature, is it correct to say that it has more heat? What do you guys think?
Yes, sir.
Okay. Well, that statement is incorrect. It's technically incorrect. Okay. So how we have now, you gotta understand ki there are a lot of things that we use in a daily life, but we know technically they are not correct. Like for example, if you say your battery of your phone is over, you actually mean the charge in the battery, right? You don't mean the battery is over. Similarly, like whenever you say serve, you just mean detergent, like everything detergent is like surf for us, and we are okay with it because it's commonly used, and it's almost like people treat it like it's correct, but it's not. Similarly here, heat is a overused word, right? The technical meaning of heat is the transfer of energy between one body to another, right? So it would be wise for us to say ki uh, if the body has more internal energy, then the body has more temperature, but you can't say that for heat, right? So you can imagine like this ki a body has more internal energy, that means it will have higher temperature, right? Another body which has less internal energy will have less temperature, right? Now when one of the bodies you know sends or transfers its energy to the other body, that phenomena is known as heat transfer. So heat is the energy that comes out of a body or is absorbed by the body. So please understand ki heat is essentially not a representation of temperature. Internal energy is, right? Heat is just a relative term uh, that signifies that transfer. Okay, it's a comparative study, or I can say it's a comparative analysis. So if I want to make it even more simple with an example, imagine you have uh, a person, only one person. Okay, you don't, so if you in a room you have two people, then you can say ki okay, one of them is tall, the other is short, right? But if you just have one person and you say ki this person has a lot of tall, that statement would not make perfect sense. That the same way it won't make sense if you say ki a body has more heat, because heat is essentially the phenomena of transfer of temperature from one body to another. So you can't that in English it might seem correct ki a body has more heat, kind of makes sense, but in physics it does not. It actually does not. It's equivalent to saying ki a body has more tall or a body has more short. It's meaningless. The tall and short are comparative study between two bodies or a relationship between two bodies. You can't use it for a single body and say ki a body has more tall or something like that, right? So
I
I
know what
hope
you mean.
huh
So compared to the initial state, suppose if the temperature of a body is increased, then it would have more heat energy compared to before. Would that be right?
more internal energy. The word you're looking for is more internal energy.
So
So
heat
the
would
body
be wrong there.
the heat statement would be wrong. Technically it would be wrong. You will see this, you'll hear this multiple different times in your life ki it has more heat. But like I said, you will also hear ki my battery is over, or my bring me a packet of surf. You won't say ki that's wrong, because it's accepted, right? So similarly, saying that a body has more heat will convey the message across, but it's not technically correct. I hope that makes sense. Okay. So that's why that's why the Kelvin scale, I'll tell you this. Okay. So let's elaborate a little bit more on temperature. Now temperature is measured using what are the different units that Celsius scale, Kelvin scale, yes? And is there any other scale that you know about?
Fahrenheit.
The Fahrenheit scale, okay. So the Celsius scale is essentially based on, see, every kind of scale that we come across in our lives will always have reference points. Okay, okay, let us call one point as 0, the other as 100, and let's make 100 divisions between them and so on. In case of Celsius scale, water seems to be the reference. Okay, so what happens is the freezing point of water is taken as 0 degrees centigrades, and the boiling point of water is taken as 100 degrees centigrade. So you have like 100 divisions in between, right? And you can go negative, and you can also get to positive as well. Similarly, Fahrenheit also works under the same principles, but it is like brine. Brine means like salt solution. 1 molar salt solution they took, and they performed the experiment. And 0 Fahrenheit is essentially the temperature at which brine freezes over, and so on, right? But the issue with this is that 32 degrees Fahrenheit is equivalent to 0 degree, and 212 degrees Fahrenheit is equivalent to 100 degrees. So although Celsius has like 100 divisions in between here, right? The Fahrenheit scale will have 180 divisions uh for the same amount of temperature difference, right? So which is 1 degree higher or 1 Fahrenheit higher? Based on this analysis, will you be able to tell 1 degree Celsius is higher or 1 degree Fahrenheit is higher?
So Celsius.
Yes, because the steps are less. Like if you have to reach the same height and you're saying, okay, I can do so in 100 steps, or you can do it in 180 steps, then if you take more number of steps, then your per unit value will decrease, right? So that's what I was trying to imply here. Now, these are the references for Celsius scale and Fahrenheit scale. But have you ever come across what is the basis for the Kelvin scale? It was invented by Lord Kelvin when he was trying to explain the internal energy. He wanted to tell कि a body, by the virtue of its temperature, or will have some thermal energy within it. And that for defining that, he came up with the Kelvin scale, which is a direct representation of internal energy and not heat. Now, if you remember thermodynamics first equation, although I have not taught, but I think you know it from chemistry, Q is equals to U plus W, right? So the heat transfer is a function of both internal energy and the work done. So you can't say कि a body that has higher temperature will have higher heat. Heat is essentially the transfer. Delta Q is the more important thing here. Okay. So anyway, Kelvin scale, if Kelvin scale is a direct representation of internal energy, then you gotta understand कि at T equals to 0 Kelvin, it would mean, like, see, you got to understand what 0 Kelvin means. It means theoretically all the particles in that gas or whatever thing you have is essentially at rest. I don't know if you have talked about this in your chemistry class, but the internal energy which gives rise to temperature comes because of kinetic energy or the random motion of molecules of gas within the container. So particles will move, and because of that kinetic energy, temperature will come. At theoretical 0 Kelvin, you're saying that the gas molecules will not have any kinetic energy of their own, and hence will stop, and hence will have no internal energy of any kind. Okay, I hope that kind of makes sense. So this is the prerequisite for understanding the thermal properties. So I wanted to make you aware of the basic concepts before we actually dive into the nitty-gritties of this chapter. Uh, so I hope everybody understood the difference between the three. Okay. I have some
So
few.
heat is the energy transferred.
Yes, heat is the energy transfer. Okay. So kinetic theory of gas. Oh no, sorry. Thermal properties. Yeah, this is correct. Now, I have a few formula-based uh, things that I wanted to share with you. The first one being this one, the conversion between the Celsius scale and the Fahrenheit scale. This is given in your NCRT, so just have a look. I don't think people are expecting you to remember the formula, but at least you should know where it came from. Okay. Okay. So here you can see again the fact that I was talking about. In the Fahrenheit scale, your temperature starts from 32 °F, goes up to 212. And in Celsius scale, it goes from 0 to 100. So the basic difference between the Fahrenheit scale and the Celsius scale is that for every 100 divisions in Celsius scale, you have 180 divisions in Fahrenheit. The equation is pretty evident. You can see F minus 32 means you're trying to neutralize the origin here. So F minus 32 divided by 180 is Celsius scale minus 0 divided by 100. So this is the formula. F minus 32 by 180 is equal to C by 100. I think 180 by 100 comes out to be something like 9 by 5 or something. Okay. Yeah, it will come out to be 9 by 5. So the whole formula becomes Fahrenheit scale mein temperature will be 9 by 5 of Celsius scale temperature plus 32. So that's going to be your baseline, or the formula that I need you to slightly at least understand at this point. If you use it consistently in any way, you will be able to memorize it. Okay. One major difference between the Fahrenheit scale, the relationship between the Fahrenheit and the Celsius scale is this, okay? And this is the comparative study between Celsius scale and the Kelvin scale. So here you can see key, although they have different origins, like Kelvin scale kind of starts at 273.15 for 0 degree centigrade, right? So and 100 degrees centigrade is like 373.15. But you will notice one thing, that both of these scales have like 100 divisions between them. So although their starting points are different, the change in temperature will always remain same, because 1 degree Celsius is equals to one Kelvin. That you might have understood from this, right? Last time 1 degree Celsius was actually greater than 1 degree Fahrenheit, but here that is not the case, because the number of divisions between the boiling and the freezing point of water is essentially just 100 for both the cases. 1 degree Celsius is actually equals to 1 degree Kelvin, right? 1 Kelvin. So that means as long in formulas where something like, for example, let me give you some examples. The ideal gas law is PV equals to nRT. T is the absolute value. Here you have to convert your temperature and plug it in Kelvin, because if you're thinking 0 degree centigrade, that means instead of 0 you have to put 273 there, because this is T. Okay. But you also remember the formula for internal energy. What was the formula for internal energy from chemistry? Nc delta T. Do you remember this formula? Yes, no, guys? Internal
Yes, sir.
energy.
So, but
Yes.
we learned it in a bit different manner there.
Was it Ms delta T or what?
So no, sir. There we just learned it that internal energy has many constituents, and we didn't exactly quantify internal energy, but only change in internal energy.
Okay. So internal energy is like Nc delta T. So here delta T is change in temperature. Okay. So the change in temperature, in this case, it doesn't really matter if you go for Celsius or Kelvin, because the change in temperature in Kelvin scale and Celsius scale is exactly the same. So what I was trying to point out is, whenever you have, because this question students has asked me, sir, when do I convert to Kelvin and when not? See, whenever you have a formula where delta T, change in for temperature is not asked, they're asking you the absolute value of temperature, you gotta convert into Kelvin. But in formulas where you are coming across change in temperature, which is given by delta T, uh, there you don't have to worry about converting to Kelvin, because the difference is going to come the same. So if your temperature goes from 0 to 50 degrees centigrade, then the difference will be 50 minus 0. That's just 50, right? You don't have to convert each of them to Kelvin and subtract them. Even if you do, it's gonna come the same. Okay. So I hope that kind of makes sense. Please let me know if you have any doubts up to here. No doubt. One more thing, before we go ahead, I'll need you to understand, or I need you to know, before we even start this, is the ideal gas law. Okay, and we'll talk about it in very much detail in the next chapter in physics, which is the kinetic theory of gas. Wahan pe we'll do it like in with too much detailing. We'll talk about Boyle's law, Charles law, Gay-Lussac law, any all the kinds of law. Avogadro's law. We'll talk about all these laws in detail. But right now, I just need you to know the formula. So PV equals to nRT. In physics, we use mu instead of n, but as long as you understand what that number stands for, or that symbol stands for, I think you will be okay. So n is the number of moles, or mu in our case, mu is the number of moles. Unlike chemistry, where you use other kind of units like 1 atm, 1 bar, and all that kind of stuff, physics will be using only standard units. So your pressure will be in pascals, right? volume will be in meter cube, uh temperature will be in Kelvin. So your there's only one value of gas constant that you need to remember, which is written on the slide here. It's 8.314 joules per mole per Kelvin. I hope all of you remember these numbers. Okay, so please note that down. uh again, there's little whenever you find questions from gas law, try to remember the basic laws uh, from your chemistry. If temperature is constant, then pressure is inversely proportional to volume. So P1 V1 will be equal to P2 V2 if temperature is constant. Now that is known as Boyle's law. Now V is directly proportional to T. This is known as Charles' laws, where if pressure is constant. So the only way you'll be messing up um, the ideal gas law subparts is if you forget to say that the other quantity is constant. Like for example, you can't say just ki haan, pressure is inversely proportional to volume and that's it. If you just write pressure is inversely proportional to volume, I think you will lose the marks, because that is not true. Pressure is not inversely proportional to volume in a gas. Pressure is inversely proportional to volume in a gas if the temperature remains constant. In an isothermal process, pressure will be inversely proportional to volume, right? So that is something that you need to be aware of. But apart from that, everything is fine. So again, go through all the 3 points that I revised here, and let us start thermal properties if you have understood everything up to here. Okay, the first thing that I want to tackle here is the concept of thermal expansion. Okay. My handwriting is visible to you guys, yes?
Yes, sir.
Okay, it's not too small, okay? Is it?
No, sir, it's visible.
Okay. So the idea of thermal expansion is goes something like this. So if you have uh, a body and you expose it to higher temperatures, and let's say heat is absorbed by the body, and you know the what I wanted to say here is that the body will expand its size. Generally speaking, all the bodies, if you increase the temperature of the body, then you will see some kind of expansion, right? And the reason for that, and the way we explain this in physics is that gases ka to theek hai, gases ke liye we will discuss that separately in thermal properties. But for liquids and gases, uh, even though we see that all the particles on a solid body are at rest, it may seem to us ki they are at rest, but at the molecular level, all the molecules are vibrating slightly. And how do I know this? Is using this concept of Kelvin scale only, right? If it has a temperature, then it is coming from the vibrations of the atoms and the molecules. So if your table is not at 0 Kelvin, if it is at 300 kelvins, then that 300 kelvins is because of some of its because of its internal energy, and then internal energy is coming out because of the the velocities and the kinetic energies of each of these particles, right? So as the temperature increases, the internal energy of the body increases. If that is the case, then the molecules will be vibrating more, right? So if the particles are vibrating more, then they will require more space. So that is the reason that is given that thermal expansion happens, and that is what is given. That is what you can see in this diagram as well, which was vibrating, right? This is the theory behind thermal expansions. Now you might have noticed one physical example of this is this. Okay, this is a picture that I took actually when I was working as a civil engineer. Do you know what this is?
So welding it to join it or something like that.
So it's like this is a railway track. Okay, so
I
uh,
think it's called thermite reaction or something.
no, you're talking about the construction of railway tracks. What I'm saying is this is the final product. Uh, you will not. So if you travel along the railway tracks, then you're gonna notice that after a certain interval, there is like a small gap in between two rails, right? consecutive rails के बीच में there will always be a little bit of gap. Can you tell me why there's a gap?
Sir, because in the summer when the temperature is high, the metal would expand.
True. And imagine if we don't provide those gaps, this is what will happen, right? Okay. So the track will sort of bend because there will be a lot of stresses developed, and these gaps are there for the thermal expansion to happen, right? So how much gap should be there? Uh, on what kind of material we are using? All of that comes into picture in this particular chapter. So I was just giving you the scope of this chapter, right? It has huge utilities in your mechanical engineering, your electrical engineering, and the core engineering where heat is involved. So anything that you're doing will have expansions because of heat. And if you don't calculate for that heat, then you have yourself an engineering failure, right? You can't afford to happen that. So these gaps are there to compensate for this kind of a high stress situation, right? So this is high stress bending. Okay, so we want to avoid that. That's why there is a gap, right? So so this is one of the practical examples. Okay. Now these thermal expansions are actually classified into three different parts. One is the linear expansion. Thermal expansion, three types. The linear expansion. The second one is known as the area expansion. Area expansion is known as superficial expansion as well. You'll see this different terms utilized in your different books. Different authors like to use different names. So this is also known as aerial expansion. There is also the superficial expansion, and so many different names they have for this one. Last one is volumetric expansion. Okay. Now, whenever I do this classification, people start believing, for some reason, I don't know, but people start believing that these three things will happen, uh, you know, on different bodies or something. But you got to understand, it's never going to happen. The linear expansion is happening and volumetric is not happening. Remember, on a body which is exposed to more temperatures, or if it absorbs heat, then you got to understand that the body is going to do linear expansion, is also going to do area expansion, and is also going to do volumetric expansion, right? Now, depending on what the question is asking, if the question is asking for the change in volume, you're going to use the volumetric equation. If they are asking for the change in, I don't know, the diameter or something, then you're going to use the linear expansion. The only way to check which kind of coefficient you need to use, or should you use the linear equation, or should you use the area equation, or should you use the volumetric equation, is just look at the units, right? uh, if it's power one, so if we are talking about I don't know, radius, diameter, length, breadth, width, height, any kind of thing that has one dimensions, uh you'll be using the linear expansion equation. Similarly, if you have areas, any kind of areas, top area, bottom area, curved surface area, then the area expansions will be given by the area expansion equation. And so finally, the volume to it is easy. You just look for that cube, meter cube, centimeter cube, millimeter cube, whatever it is, right? So without further ado, let us jump into the first segment, which is the linear expansion. I have a diagram for it. So it's an exaggerated diagram. Please do not misunderstand, right? I'm just making it here so that you can understand. So I need you to draw all of this in your copies as well, right? I'll be sharing the notes, but when you do it on your own, there's always you'll always be able to understand better when you are revising. Okay. So okay. So like I said, this is an exaggeration. It's not the actually if 1 meter long rod won't become like 1.5 meter or something when the temperature is increased. The actual increase is like really, really less, and we'll talk about it actually. But I need you to know the notation here. L represents the original length. This is the original length of the body. Okay. Your LF, if you ever see this, okay, usually original length is represented with L with a subscript O. LF is final length. Can you tell me what is delta L? It's actually LF minus Li. So delta L is essentially the change in length, okay? And that is alpha LF minus Li, and this is known as change in length. This is known as change in length. Okay. Now this is the equation. I'll tell you, this is the experimental equation for increase in length. You say that the final length is actually initial length plus delta L, right? Now you got to understand is that delta L can be written as L initial into alpha into delta T. Okay, now I'll explain what these quantities are. So you're saying the change in length is equals to original length. Why am I using Li? I'm using different symbols at different locations. So let's use LO. LO is the original length. Okay. Let me erase this actually. Don't want to create any confusion. Okay. L naught is the original length of the body. Here also I'll put, where did it go? Here also I'll put, this is L naught. This is L naught. Okay. Just to make sure, okay, there is no confusion. So L naught into alpha delta T. So what I'm saying is this delta L, this extra length, is the original length multiplied by alpha into delta T, right? So this everybody knows this is what the original length, and alpha is this has a special name. This is known as thermal coefficient of linear expansion. Okay. So alpha has a name. Alpha has a name. And that name is thermal coefficient of linear expansion. Okay. So what is delta T? Delta T is change in temperature. Okay. So guys, understand what does this mean? Okay. This means ki, if you know the thermal coefficient of linear expansion, and by the way, this coefficient is a function of the material. It does not depend on geometry. So if you have a ball made of steel or a bat made of steel, both of them will have the same alpha because it's dependent on the material and not on the geometry of the body. Okay. So both steel by default will have some value, and anything that you make out of steel is going to have the same thermal coefficient. Okay, will have the same thermal coefficient. Now question is, can you make it a little bit simple? So LF minus L naught, you take L naught to the other side, it becomes LF minus L naught will be equals to L naught alpha delta T. Okay. Now what is LF minus L naught? L naught, this is nothing but delta L. Delta L is L naught alpha delta T. That's what I had written there. Okay. Delta L by L naught will be equals to alpha delta T. Now, can someone tell me what is change in length by original length? This we have studied somewhere else in physics.
So strain.
What? This is known as strain. And because it is coming from temperature change, this is a special, you have a special name for it. You call it thermal strain. Okay, so the linear thermal strain that is created is equals to alpha into delta T. If you remember that much, you can write, you can solve any kind of question that comes in linear equation, linear expansion, right? So I hope everybody is clear on how to figure out the final length if I give you a temperature increase of some regard. Okay.
So what does alpha represent? Like, does increase in alpha mean increase in expansion or something?
Yes. So alpha is a representation. It's a number that's going to represent how susceptible the length of a body is to temperature changes. So if alpha is more for a body, that means it will expand more for the same amount of temperature change, right? So if you have steel and let's say copper, and I don't know the exact values for both of these, I will tell you. But let's say ki steel ka more, steel ka alpha is more than copper. Then you know ki if you heat them together, then steel will expand more compared to copper. I hope that answers your question.
Yes, sir, got it.
Please note this down. Okay. Now, the next kind of expansion that I am going to talk about, and I want you to, take a guess. Okay.
So in the previous one, would Young's modulus be applicable or no?
Yeah, it is applicable.
So because
If
the
you,
temperature changes.
it will be applicable. See, the thing is, delta L by L is alpha delta T, right? So you can go a little bit further and think more about this. Like now that I have the strain delta L by L naught, uh, how do I get stress? Do you remember? Well, Young's modulus multiplied by strain is stress, right?
So
Right?
but would Young's modulus change with temperature?
Young's modulus, again, see, in reality, there's a lot of things that going to change. Alpha itself is a function of temperature, right? But for any given, range of temperature, you can pretty much assume alpha and y to be constant for small temperature intervals, right? What I'm saying is, even though it's variable, we have the mathematical tool of integration. So even if it's variable, it doesn't really matter. But what I'm saying is, if you multiply this delta L by L with the Young's modulus, you're gonna get stress, and that stress is known as thermal stress. You'll read about this. Okay. I think you'll also have a question based on this. And we'll also solve we'll solve that question when we reach there. Okay. But yeah, remember, Young's modulus multiplied by strain will give you stress. And we have already figured out what the strain is. So Young's modulus into alpha delta T will actually be what? The thermal stress. This will be the thermal stress. Okay. I hope that makes sense. Right. But there's one thing that you need to understand, whoever is thinking about thermal stress, is that if you have a body and you just increase the temperature, the body increased in size. There will be no thermal stresses generated within the body. Finally, can you tell me why? Because you are free to move. See, stresses come whenever like the body wants to expand, but you have not allowed it to expand. So the body has a lot of stress, right? It wants to extend in size or it wants to contract in size. That is when stresses are developed within the body. If you remember solids, the body used to have like an original length, and you increase the size of it and it wants to go back, right? But as you increase the temperature here, you gotta understand that the original length is L plus delta L. That is the new original length. Now, stresses will only develop if you have like let me draw it here so that you're able to understand. If you have just one rod like this and you heat it up, what will happen? The body's size will automatically increase like this, and we're not worried about it. Zero stress. The body has zero stress. Even though the length has changed, it has zero stress. Now the same body, under the same scenario, you start heating it between two walls, and you want to heat it, but the wall is preventing it from increasing in size. So this is this extra length L delta L, which was supposed to be alpha delta T. Okay, delta L by L, which was supposed to be alpha delta T, is now the, how can I say this? This is the strain that is created within the body, which is going to be responsible for a stress. The body, because of its increased size because of the increased temperature is now uh, wants to expand but can't because it is blocked from both sides. So there is internal stress forces that have generated within the body, and that is the reason why things bend, right? Now, in the picture that I had showed you before, same kind of thing was happening. If you have two rail lines, blocked, and there's no space for it to expand on its temperature, then what will end up happening is that this thing will just go like this. It will bend up, it will bend like this. Okay, or maybe downward also, that is also possible. So that bending happens because of thermal stress. Okay, so all of this will be required, we'll be talking about this very soon. But okay, little bit of information, extra information doesn't hurt, right? Now, this is known as, the first was the linear expansion. This is me talking about the linear expansion. I'll write it in the bottom. This is linear, this is linear expansion. Okay, now what I'm going to write or solve next is the area expansion, and the concept is very easy, and it's essentially the same, right? So the final area of a body will be the original area plus change in area, right? That is nothing but equals to original area plus beta into delta t. So you can see in the earlier equation it was alpha delta t. This time this is beta delta t. So beta will be known as what? Take a guess. Tell me what beta will be known as. What will be the name of beta?
The coefficient of areal expansion.
Yes, this will be known as the coefficient of area thermal coefficient. Don't forget to use the word thermal. Thermal coefficient of linear expansion, or thermal coefficient of area expansion in this case. Some people also call it superficial coefficient. Okay, so thermal superficial coefficient means the thermal coefficient of area expansion. Now, in here, I can simplify this and I can say ki, okay, let's say ki AF minus A naught is equals to A naught beta delta T. So you'll be saying ki this is delta A by A naught is equals to beta into delta T. So, okay, so this is the equation. This is the equation. Okay. But I would like to show you one thing. Okay, so after you have written this, I need you to show something. Don't write. Just uh, see what I'm doing here. Okay. So let us take a very simple scenario. Let's say that I have a rectangle. Okay. The length is L and the width, let's say, is B. These are what kind of dimensions? Are they uh, linear dimensions or like two dimensions? They are linear
It's two
dimension. Like each,
dimension.
no. The total overall is two dimension. What I'm asking is length and breadth. They themselves, like individually, they are linear dimensions. They are linear dimensions, right? So when you heat this body, the length is going to increase and the length is going to become L plus L alpha delta T. Everybody is comfortable with this, yes? Okay. What happens to the width? B plus B alpha delta T. Because again, I'm not using beta, because I would be using beta if I was talking about the overall area. Let's say this original area is A naught, this area is A final, then you'll be saying something like that A final became what? The A final is essentially A naught plus A naught beta delta T. I hope this makes sense, right? Every linear dimension in the body will increase by alpha delta T. Okay, the linear strains that will be created is alpha delta T. However, area ka expansions may you'll be using A naught beta delta T. I hope that kind of makes sense. Okay. Now there's a relationship between alpha and beta which I'd like to explore. Okay. Can I say, and you be realistic with me, can I say that A final is nothing but L plus L alpha delta T into B plus B alpha delta T? Can I say this? It's a rectangle, so area is like length into breadth, right?
Yes, sir.
Okay. Now you gotta understand, I'm going to multiply this inside. So this is L into B is how much? Well, LB. What will be the second term? LB alpha square delta T. This is another term. What other terms get you? So I multiply this and this, then I multiply this whole term with this whole term. Now the time is to multiply like, so you'll have like 2 times of LB alpha delta T. Check whether this expansion is correct or not. Take a minute. Don't copy it down. Try to do it on your own. You'll understand better. I just open the brackets. I multiply each term with each term.
Sir, delta t whole square, no, sir?
Oh yeah, delta T whole square as well. Yes, any other mistakes, please check. Okay. Now I need you to see something. Okay. This is a table from your NCRT. This is a table from your NCRT. 1 second. Let me take it to a different page. This is good enough. Can you see what is given to us? What is this table of? What is this table of? Is the value of linear expansions. Okay. Can you tell me what is the value? What is the coefficient of linear expansion for iron here? It's 1.2
It's
into 10
1.2.
1.2 into 10 raised to power minus 5. Notice this on top. This is given in 10 raised to power minus 5 Kelvin. All the alpha values, like you have to multiply this with 10 raised to power minus 5. So what I'm trying to say to you is, usually the range of all the alphas of the materials that we deal with is in the order of 10 raised to power minus 5. Okay. Now that is fine. That is fine. But when you like, what is L into B? This is original area, right? L into B is what? Original area. So I'm going to write it like this. This is original area plus original area alpha square T square plus 2 times of original area alpha delta T. Okay. Now, if you take original area common, or from the something like this, or where's the eraser? From all the 3 terms, will you get 1 plus alpha square delta T square plus 2 times of alpha delta T? Can I say this, guys? Now, I need you to notice one thing. Alpha square value will be in the order of what value? Because we have already understood that alpha is in the range of 10 raised to power minus 5. So alpha square will be in the range of what?
10 power
10 power
minus 10.
minus 10.
You got to understand, I'm trying to add 1 to 10 raised to power minus 10. What can I say about this particular? Okay, we're going to neglect alpha square, because if I'm trying to add alpha square to 1, then you are trying to add 2 numbers which are like 10 times bigger than one another, right? So that addition will so this value will be pretty much negligible with respect to 1, right? So you can say ki AF is essentially just A naught 1 plus 2 alpha delta T, because you have ignored that term. So you say ki AF is equals to A naught plus 2 A naught, sorry, I'm multiplying back A naught inside. So A naught into 2 alpha delta T, right? Compare it to this equation and give me what is the value of beta. Compare to the original equation and tell me how much is beta.
So we don't neglect the 2 alpha delta t.
No, because in that case, you'll just end up with final area being equals to original area.
Yes, sir.
Okay, there is a little bit of change, right? I want to take that small change that happened. but it should not be like 10 raised to power minus 10. That will not be visible, right? Compared to alpha also, alpha square is like 5 times 10 to power 5 times bigger, right? So it's not just one I'm worried about. In front of the other two alpha term also, alpha square becomes negligible, right? So that's why I'm able to neglect, because in this addition of 1 plus alpha square plus 2 alpha, alpha square is negligible compared to both the other terms that we are looking at. So from there you will get beta is equals to 2 times alpha. Everybody is clear with what I did right here? If you have any doubts, again, I'll give you a little bit of time to analyze this, and let me know if you have any doubts. So take 2 minutes to understand this derivation. This is from your NCRT, and it can come in your school exam. So go ahead and please practice this once. So look at the derivation and try to do it on your own in your copy. Okay, it's a very easy derivation. So it can come. It has a very high probability in coming in your school exam. So you can pretty much try this. Okay. Now, this equation that I had written before here, this can now be modified, and it can be written as delta A by A naught is 2 times of alpha delta T. Okay, so this is another equation that you can remember. So please let me know if you have any doubts in this. Yes, no doubts.
No doubt, sir.
Okay. This kind of a question you'll also find in NCRT. This is how the question looks. So can you check the question out? This is what the question says. Show that the coefficient of area expansion of a rectangular sheet of solid is twice its linear expansion. So this is the question we just solved right here. Okay. So you can see this is adhering to this NCRT. So it's very important understanding this is also vital for you to be able to solve JEE mains level questions or competitive level questions. So pay attention to the derivation. Okay. Now, the same thing, we are not going to prove it for volume, but it can also be told about volume. Okay. Uh, this is the diagram I wanted to show you for volume. Again, let me tell you, these diagrams I was just making it a little bit funny looking. Okay, so you won't have like a vessel, and if you put it on the, so you bought like a 3-liter cooker, and when you put it on the gas, it becomes like 4 liter or 5 liter. It doesn't happen. It's just an exaggeration that I have created here. So it looks a little bit fun to look at, but honestly speaking, the change in what, because you saw the value of alpha, right? 10 raised to power minus 5. So even if you go like 1000 Kelvin, uh like alpha delta T, let's say you change the temperature by 1000 Kelvin, then the alpha into delta T value will be 10 raised to power minus 2, right? So delta L by L is 10 to power 1 by 100. So it's like 1%, right? So even after you change the temperature by 1000 kelvins, now that's very huge. 1000 degrees centigrade, say, if you change the temperature, the amount of strain generated in the body is only 1% of its total length. Okay, 1% of its total length. 1% of his total volume, or 1% of his total area. So these are not big changes. It's 1% change is what you will not even notice. 1% of the volume changed. Okay, so that means a 1 liter max 1 liter container will become like what is 1% of uh what is 1% of 1 liter?
So about 10 ml.
10 ml, right? So if you increase the temperature by 1000 kelvins, then your container, which is, I don't know, 1 liter, will become 1 liter 10 ml, right? So that is a barely noticeable. You'll barely notice it. And I don't even know if it will survive like 1000 Kelvin increase in temperature. The vessel itself might melt.
So I have a
Okay.
doubt.
Yes.
So you told that alpha value is temperature dependent. So practically, by how much would alpha value change when we would change the temperature?
Okay. Let me complete this one. The next concept is that only I'll talk about it. Okay. So V final is original volume plus original volume into gamma delta T. Okay, so this is what I'm looking at. This is volumetric expansion. The final volume minus initial volume is going to be V naught gamma into delta T. And you can say ki delta V by V is nothing but gamma into delta T. Can you take a guess what gamma stands for? Or what do you call gamma? Thermal coefficient of
Volumetric
Volume.
volume.
expansion.
Volumetric expansion. So delta V by V is equal to gamma T. And also one more thing, gamma is actually 3 times of alpha. Okay, value wise I'm speaking. So it's not necessary for key. If you have a piece of steel, you have to define alpha, you have to define beta, you have to define gamma. As long as one of the coefficient is known, then all the coefficients are known, because your area expansion is 2 times of linear expansion and volumetric expansion is 3 times of linear expansion, right? So that is what happens here. And I'm going to talk about the concept that you guys are asking, which is what happens to the value of alpha? Is it constant? Well, if the temperature range is not too high and nothing is mentioned in the question, please assume that these thermal coefficients are constant of sorts, right? So only in questions where they specifically mention ki your alpha value is not constant and it's a variable, there you should take your help of calculus and all that stuff. But 99% of the question alpha will be assumed to be constant for low temperature variations, right? However, in reality, this is what happens. Okay, then this is again for from your NCRT. Uh, read the concept or the keywords at the bottom. It says coefficient of volume expansion of copper as a function of temperature, right? So you can see here that as the temperature of the body increases, you also see an increase in the value of alpha, right? What does it mean? It means, and I think I have discussed what alpha is in the beginning only, like what is the sense of it. So it's the rate at which the expansion is happening. So see, if I ask you this simple one question about copper. Let's say copper was at I don't know 50 degrees centigrade, and I made it 60 degrees centigrade. So what is delta T? 10 degrees, right? It is 10 degrees. Okay. And it will correspond to some increase in length. Now, if I go like, okay, I change the temperature from 1050 degrees centigrade to 1060 degrees centigrade, then again, delta T is still what, 10 degrees only? Will it give the same amount of expansion? The answer is no, because at higher temperatures alpha values themselves will increase. So at higher temperatures the expansion will also increase for the same amount of temperature difference. I hope that statement kind of makes sense. Please let me know if you didn't understand it.
Got it, sir.
Okay, so let me repeat though one more time. Let's say okay, I have a piece of copper that is given to us here, right? What I'm saying is if I go from 50 degrees to 60 degrees, the copper's length will increase. Obviously, it will increase by some value. Now, the same piece of copper, if I so say ki the temperature is 1050 to 1060, again 10-degree difference, the copper will rise in size. But what I'm saying is the expansion in this case will actually be higher, because at higher temperatures the alpha values will increase as well, right? So I hope I'm able to clear your doubt on this. You can see that as the temperature increases, the value of alpha will also increase. So the rate at which the expansion happens for a given temperature difference is going to remain the same. Please let me know if you have any doubt.
So after
Okay.
reaching a certain high value, it reaches a limiting point, or is it just that the graph is drawn to this temperature range?
After a certain point, the change in alpha also kind of becomes lesser. Okay, so it's almost tends a value. So based on this concept, can you do this question? Now I could give you a simple question. I will actually do some simple questions, but I'm giving you a little bit of difficult question to start with. Okay, sorry about it. I should have actually given you some easy questions to begin with, but I feel like you should be able to do it because I was just discussing about what alpha is not necessarily a constant. This is a question jahan pe alpha is a function of temperature. It is not it is not constant. You can see that if you put 100 Kelvin, you'll get a different value of alpha. If you put 200 Kelvin, you'll have different value of alpha. So how do you figure out what is the expansion on a 1 meter rod?
So here change in length has to be found out.
Yes, Rishi, one more time.
So here the change in length has to be found out.
Yes. You have to find out what is the expansion that is happening. Give it a go. Sixteen into 10 raised to power minus 4. Let's see if that is correct. Hmm. 16. No. How did you do it? Can you explain how you did it? The answer is not correct. But yeah, let me know how you did it.
Sir, I was confused whether I had to substitute 200 or substitute 200 and 100 and maybe find the difference. So
Hmm.
I first substituted 200
Hmm.
and now I can try maybe subtracting the two.
Hmm.
So would it be
Well,
meaningful to integrate?
that's what I was indicating at. See, you can't plug in values here because you gotta understand that for every temperature, like what about okay, you're considering 100 and 200, but what about 150? There also alpha will be different, right? At 120, the alpha will be different. So the only way we can proceed with this is if we consider differential changes in temperature. Like you have to consider, you have to write the equation ki chalo dl delta L by L is equals to what? Alpha delta T, right? Now this is usually the equation, right? But if I want to write it in the differential format, like for small change in length, so I'll write ki change in small length, okay, by the original length, okay. uh, I should actually write it like this. This is L naught, okay. So this is dl, small change in length by the original length, is equals to alpha into small change in temperature. Now I think you should be able to solve this. What do you do next? You plug in the value of alpha here, right? You say ki dl by L naught is equals to what? 2t plus 3t square dt And don't forget the 10 raised to power minus 8. I can take it outside actually. I'll just write it 10 raised to power minus 8 because it's a constant. It doesn't really matter during the integration. Now, if you integrate both sides, right, then 1 by L naught comes out and then you have change in length, right? Remember, L naught is not, you don't try to integrate this on the left hand side. And the reason for that is this is not L. This is not a variable. L naught is not going to vary with respect to time, right? So, or with respect to temperature. L naught is the original length. Original length to utna hi hai na? With higher temperatures, you will have like more and more change in length, but the original length was always the same. So 1 by L naught into delta L. And on the right hand side, what is the integration of 2t? I think it will be t square by 2 and 2 and 2 cancels. What will be the integration of 3t square? I think it will be t cube, right? And what are the limits on your temperature? You go from 100 Kelvin to 200 Kelvin, right? Now, L naught is 1 meter, so I'll just plug in the value of 1 meter here. That's given in the question. So your delta L will be t square plus t cube, 200 Kelvin and 100 Kelvin into 10 raised to power minus 8, right? Now, do you remember how to plug in the limits in an integration?
So first the upper limit, then subtract the lower limit.
So you plug in 200 here, so this will be like 200 square plus 200 cube, right? And then you subtract 100 square plus 100 cube. So if you do this, and don't forget, after you do all of this, you have to multiply with 10 raised to power minus 8. Okay. It comes out to be 0.07 meters. Approximately this much, 0.07 meters. Okay. So I hope everybody understood what I did here. Please let me know if you have any doubts in this. Okay. Now let us also do some easy question. This is a little bit of trickier question. This is a tricky question. I'd like to take up some questions on the easier end of things. Okay. 1 second. Let me see if I can find some questions from. You can use the calculator. I mean, for the first one question, 1 or 2 question, you can use a calculator if you want. There's one question that I want you to try. Can you try this question, guys? Everyone needs to try this. This is a very easy question. Now, this is one major confusion among students that, sir, if I have a metal and if I have a hole in the metal and if I increase the temperature, guys, tell me what happens to the size of the hole. First question, does the size of the hole increase or decrease?
It'll increase.
Anybody thinks who thinks this is going to decrease, because as the metal is increasing, the size of the hole should become less? Is there anyone who feels like that? Okay, the answer is the size of the hole will also increase, because see, the size of the hole will decrease is if you have like if you constrict it from all different sides and you're not allowing this to increase, then there's a possibility ki the size uh, might not, it might not increase. But you gotta understand ki this is if it is free to move. If it is free to move, guys, then there is no doubt that all of the particles will try to move away from one another, even the particles which are around the hole. Okay, what I mean by that is, if this is the plate we are talking about and this is the hole, all the particles which are, part of this periphery here, they're also trying to move away from one another because of the increasing temperature. If that is the case, then it cannot contract like this, because if it contracts like that, that means the particle has come closer. So with increasing temperature, any kind of hole size will also increase. Now, that being said, you have to directly use the formula for this question. Gentlemen, ladies and gentlemen, you have to just use the final formula for this equation. It is given to us that the diameter, the initial diameter is 1.2 centimeters. I'll write D naught. Okay. Let me erase this. Okay. Let's say this is your initial diameter, original diameter. And the temperature during this time is like 20 degrees centigrade. Okay. So we have to find out what is the final diameter. So the formula is final diameter is original diameter plus original diameter into alpha delta T, right? So I'm going to write 1.2 plus 1.2 into 19 into 10 raised to power minus 6. And the temperature has changed to by how many kelvins? 200 kelvins. Okay. Now again, I have said you don't have to convert it into Kelvin and then subtract. The subtraction or a delta T change in temperature will be same in both the scales, right? So 200, if you multiply this, I think you're gonna get well, I have to bring out my calculator. So 1.2 into 19 in 0 into 200, 4560. 1.2 into 19. So this is like 1.2 plus 4560 into 10 raised to power minus 6. So 1, 2, 3, 4, 5, 6. So this is 4 digits. So 1.2 plus 0.0456. Is this correct? 6 zeros. 1, 2, 3, 4, 5. Oh, I think there's one more zero here, right? One more zero here. So this becomes 1.20456. So this is the new diameter, final diameter. Everybody got this? Please let me know if you didn't understand any part of this. I'll explain. By the way, this is in centimeters. Remember, don't have to, whatever units you choose for these two quantities, D naught, right here, I chose it at centimeters. So that's why my final answer is also in centimeters. Okay. Everybody did this question?
Yes, sir.
Another question, another little bit theoretical question. Check this out. Try this question, guys. AB, what happens if I heat this plate that has two holes? What happens to AB and what happens to BC? The two lengths. AB increases, BC decreases. AB decreases, BC increases. Both of them increase, yeah, both of them decrease. These are the four options you'll get. The question is very, very simple. Again, I'm asking, if you increase the temperature of a plate that has two holes, what happens to the size of AB and the size of BC? Both of them increase, both of them decrease. One of them increases, the other decreases. AB increase, BC decrease, or BC increase, AB decrease. Tell me, guys. Tell me what you think. Well, the answer is both of them will decrease. Okay, there is a I've seen a lot of people do this mistake. They say, sir, BC will decrease because AB is increasing, right? Again, I'm telling you the same concept. It's not that the size of this body is limited. So if let's say the holes are increasing in size, then the gap between them has to decrease. That's only if all the sides are like closed and it is not able to expand wholly. But what I'm saying is thermal expansion is not like that. It's like the expansion is happening such that all the particles are kind of moving away from one another. So that means both the dimension, both the linear dimensions will increase no matter what. Okay. So I hope you understood that question as well. If you have any doubt, again, please ask.
So when a plate expand, would it expand from both sides, or would the expansion be directed towards a particular direction?
Can you repeat your question? I didn't understand.
So suppose when a plate heats, so would it expand both sides, suppose left and right, to with the same extent, or would it be that it would expand towards one direction more or less?
If it's a isotropic material which is like uniform on all sides, it will expand at the same rate. Okay. What I mean by isotropic is like the density of the material or the material that we have used is uniform throughout. Copper only, like completely copper. Then and it's a stick. Then if you hold it in the middle and you have like uniform temperature across all the bodies or all the part of the body, then the extension will happen in both the sides at the equal rates. It also depends on see when indirectly it kind of depends a little bit on the density as well, because the rate at which you can heat something kind of depends on the density of the body, right? So although there is no direct relevance with alpha with the density of the body, but the change in temperature, if you can make sure that the change in temperature in all the locations of the body is like equal, it's like when 1 degree changes on the left hand side, 1 degree changes on the right hand side at the same instant, then yeah, then your analysis is correct. I hope that makes sense.
Yes, sir.
Okay. Now I have another question. Let's do one more question. I think you can squeeze in one more question. So this is a mains question. Let's see if we'll be able to do this. So they have given to us how much is the length increase percentage. And what they're asking is what is a change in density? Okay. So can we try to figure it out? Little bit of out of the box thinking you have to have. You have to also remember a little bit from units and dimensions, the first lecture in physics. A little bit of error analysis we did. So वहां से थोड़ा सा concepts you will need here. But it is the easy one though. Now I understand some of you might have forgot everything that you studied in units and dimensions. So for them, I need you to revise a little bit occasionally so that you don't forget everything that you are studying now, right? If you don't revise at all, you'll forget every single statement that you have studied today after 10 days, right? But if you keep on revising, you can remember pretty much everything, at least not everything, at least like 80% of things you will remember, right? So before the exam, if you do little bit of revision, you're ready to go, right? And all of this is coming after 2 years, so make proper notes. Yes, anybody found out how to do this? I have one answer. Rishi says 0.06. Can you tell me how you found this?
So
Answer
I
is
use
correct.
the concept that gamma would be 3 times of alpha.
Awesome. Awesome. Perfect. Then
And then I calculated delta V by V, and I landed at this answer.
okay, cool. So yeah, we know delta T in our case is 10 degrees, right? And we also know in the question it is given that length is increasing by 0.02 by 100. Percent means like 0.02 by 100, right? So strain is also known. Now, if you use the equation delta L by L is equals to alpha delta T, then 0.02 by 100 is equals to alpha into 10. So that means alpha is how much? It will be 0.02 divided by 1000. Now we need percentage change in density. For that, I need change in volume by original volume. That is nothing but 3 times of alpha delta T, right? So that is 3 times of 0.02 by 1000 into delta T, right? Which is nothing but 10 degrees. So 10 cancels. You have like 0.06 divided by 100. So that's like 0.06%. Now, I have found out the change in volume by original volume, but you got to understand from error analysis that now if you remember something like this, let's say Z equals to A by B. Do you remember how do you find out delta Z by Z? This was equals to delta A by A plus delta B by B. This is there in error analysis. You can just quickly revise if you haven't read through my lectures on error analysis. This is available on the Learnist as well, right? So delta Z by Z, same concept here. We know density is mass by volume. Now mass is not changing. Mass is not at all changing. So change in density by original density will be change in volume by original volume, right? So this means whatever change or percentage you have found for delta V by V will also hold true for delta rho by rho. Okay. So that's why option number A is correct. Option number A is correct. So let me know if you have any doubts in what we discussed till now. Okay. And let's meet after 15 minutes. Let's take a quick snack break. And I'll see you on the other side. If you have any doubts, again, feel free to ask. I'm here. Hi guys, welcome back. If you're back, you can start solving this question. This is a mains 2020 question. Anybody found the answer to this question? Okay. Been waiting for a while. Some people left or what? I don't see Rishi. Rest of you guys, anybody did this question? Come on, let me know. Kartik, Ishani, Medha, Purva, Ritika, Ritu,
Here
Shrishti.
I'm stuck at a specific step.
Okay. What about others? Ishani, what do you think? Shrishti, what do you think?
So I'm just solving it on last step.
Okay. Let me give you a hint. Okay. So what you need to do here is Purva is still trying. Okay, cool. What about Ridya, Medha?
So I'm not getting how to approach this.
Okay, cool. So I'll give you a little bit of hint. See, the approach comes. Medha, sorry, who was saying? Ridya. Ridya was saying, okay, approach. I don't know. Approach will come as you do more and more questions. So, this is the first question that you have attempted, and it's directly a JEE main level question. So I completely understand if you are struggling with the approach here, right? And it's expected that you'll be struggling with the approach. But the more questions you do like these, and every questions will be different, to be honest, every question will be different. But once you do like a lot of questions from a particular topic, you will be able to gain the necessary experience required to essentially solve a question like this one, right? So you'll have to do a bunch of different questions to be able to finally get how to solve these kind of questions. But anyway, so what it is given is okay, one second. Two wires L1 and L2, okay, are joined end to end. The effective temperature coefficient of the end to end. So if I draw the diagram and let me know. So the way to approach a new problem like this is to first understand the diagram. So if I have something like make a diagram, this kind of makes it more possible for me to visualize what is going to happen, right? So I have two wires whose lengths are like original length is L1 and this one's original length is L2. This is given to us, right? And the linear expansion coefficients are also given, like this is alpha 1, this is alpha 2. The effective temperature coefficient would what would it mean? It would mean that if you had one wire that was whose length was like L1 plus L2, what will be its alpha, so that the extension in length that is happening on this wire would be same as like the combined wire system. I hope this analogy makes sense, because if this makes sense, then you will understand the solution. If you don't understand what I'm talking about, please let me know. See, you have two wires, one is L1 alpha 1, the other one is L2 alpha 2, and because of increasing temperature, there will be an increase in the overall length of the wire. Some of it will be contributed by L1 and some of the increase in length will be contributed by L2. I'm looking for a value of alpha net for which this entire rod, the rod whose length is like L1 plus L2, will have the same extension as that of L1 and L2 combined. That is the effective temperature coefficient of linear expansion. So what they're asking is what is essentially alpha net. So my first job is to figure out how much this is, right? So this delta L overall will actually be how much is the extension in 1 and what is the extension in 2. How many of you understood this equation? It's a pretty easy equation. I'm saying that the net increase in length of these two wire combination will be the extension in wire 1 plus the extension in wire 2. Now using the formulas, this is delta L1 is going to be L1 alpha 1 delta T, right? And this will be L2 alpha 2 delta T, right? Now let's talk about this combined system. In this combined system, the delta L will be L1 plus L2 into alpha net into delta T. Now what do I need to equate? I need to equate this to the addition of both of these, right? Yes, Ishani. Then you will have L1 plus L2 into alpha net will be equals to what? L1 alpha 1 plus L2 alpha 2. So from here, the net expansion coefficient will be L1 alpha 1 plus L2 alpha 2 divided by L1 plus L2. Tell me if you have any doubts in what I did just now. Okay. So again, don't worry about, the questions as of now. So this is the procedure. Like if you want to understand or if you want to get accustomed to doing questions, first start with something like NCRT. Do all the NCRT in-text solve questions and the back of the exercise books if you're struggling with the approach or how to do different kinds of questions. After you're done with NCRT, go for the solved questions in your module, right? The solved questions, then maybe the unsolved questions, right? Now you got to understand key on the Learnist platform from where I send the assignments. If you go into the JEE physics section, at the bottom of the JEE physics section is the solution to all your module. Now it's been there, but I don't know if all of you know about this. The like your module solutions to the questions are there on Learners, so you can always take up the unsolved questions and look up the Learners for its solution, right? You can also refer to any of your reference book. The standard reference books also have a lot of solved questions, like DC Pandey. You can refer to HC Verma. Don't refer to a lot of books, just take one up and do all the solved questions in there. That will also help you approach questions. And the last but not the least, the most important importance one are the PYQs, the past year questions that came, right? So if you do, so all in all, if you're able to do like 150 questions from every chapter, all of these combined, like you don't have, see, your model itself contains more than 400-500 questions in a single topic. I don't need you to do all of them, right? Choose every alternate question or every second alternate question. Just keep on doing that till you hit that 150, around 150 mark, where you become decently comfortable in the topic to be able to attempt all the JEE mains level questions. So this is what the the process of preparation is. So try to do as many questions as you can, and it will help you a lot. Even if you're attempting only your school level exams, if you do 150 questions, you will be way ahead of your peers in school. Okay, so that's how this question is done. Please let me know if you have any doubts in this. Okay. I also send out assignments that you can try. So after you have done your NCRT, just before the module or after the module, you can also do the online assignments that I send in. If you do those online assignments, again, you have a decent hold. If you're able to secure good marks in those assignments, because those are marked and it has a time limit. So if you are able to score good marks in them, then again, you're in a very good position. Okay. Now, next thing I want to teach is essentially, wait 1 second. I forgot what to teach. So I have talked about thermal. Okay, this is over, this is over, this is over. Yeah. I want to quickly talk about something a little bit different from what we have done till now. About the it's related to expansion only, but also like a little bit of different. Okay. Don't look at the graph for now, just follow the theory along with me, and I'll bring the graph in a bit. Okay. So what happens? So if I consider something like water, right? Then we know that as temperature increases, volume should also increase, and the reverse is also true. So if you keep on decreasing the temperature, the volume should decrease, right? But if the mass remains same and the volume keeps on decreasing, what happens to density? What happens to density of water? If volume keeps on decreasing for the same mass, density is mass by volume. So that means as the volume decreases, density should keep on increasing. So colder water will become heavier and heavier and heavier. The density will keep on becoming more and more, right? So that you can see happening here. You can see as the temperature on the x-axis goes from 100 to 40 to 20 to 0, the density keeps on increasing, right? But there is a small anomalous behavior. What is anomalous behavior? Like it's not following the pattern, and that pattern is that the highest density of water, according to our logical perspective, should be at 0 degree. That means 0 degree is the among 0 to 100 degrees. 0 is the lowest value. So at the lowest value, 0 degrees, you're supposed to have the maximum density. However, that is not true. Okay, in real life, it's not true. It's because the maximum is coming around something around 4 degrees centigrade. 4 degrees centigrade pe you get the maximum. This is known as the anomalous behavior of water. And Amolous. Maybe I think this is the correct spelling. Let me quickly check. Anomalous. Anomalous. It's correct. So anomalous. This is known as the anomalous behavior of water, right? This is what is the anomalous behavior of water, especially from 0 to 4 degrees centigrade? When the temperature is increasing, volume is supposed to increase and density is supposed to decrease, but that does not happen for some weird reason, which your chemistry teacher will explore. From 0 to 4 degrees centigrade, the density actually increases, and beyond 4 degree again it starts decreasing, right? So the graph goes, so this is 0 degree, this is 4, and this is like, I don't know, 10 degrees and so on. So the graph goes something like this. So the maxima is at 4 degrees centigrade. So water is dense, most dense at 4 degrees centigrade, and actually 0 degree water is actually less dense than 4 degrees centigrade. Now you're like, sir, why are you telling me all of this? There is a phenomena that helps aquatic plants and animals stay alive, right? Even though you have freezing temperatures above in the sky, the lake does not completely freeze over. Okay. Why is that? Well, you might have done this in 9th standard. First thing is that, see, let's say the lake starts from 27 degrees centigrade, and you have like freezing temperatures on top. So the top layer becomes colder, right? But we know cold water is dense, so it goes down and the warm water comes up, and the process keeps on happening. The colder water keeps on getting colder slowly and slowly, and it goes down. Then the hot water comes up, and then again it freezes. So it doesn't freeze over. I mean, the temperature decreases and keeps on going, happening like this up to 4 degrees centigrade. Now, if there was no anomalous behavior, what will happen is, as soon as the layer above 4 degrees centigrade becomes, I don't know, 0 degrees centigrade or something, or maybe 2 degrees centigrade, that layer should fall down and 4 degrees should go up. But that does not happen because the maximum density is around 4. So 2 degrees centigrade water, even though it's colder, it still remains on top. It doesn't cycle to the bottom. And that is the reason why, even though the top layer of the, of the fluid freezes over, the bottom layer always remains in 4 degrees centigrade. And that is why fish and plants at the bottom do not die, because you have like 4 degrees is enough to survive for some animals. Okay. So the plants, the aquatic plants and the fish is able to survive because the lakes do not freeze completely. Only the top layer freezes, and then since the maximum density is at 4, the colder water does not flow downwards, and the convection cycle does not continue, is what I'm trying to say. Okay. Now this is a very how can I say, fine phenomena, because of this one small density issue, variation. You have all these aquatic plants and animals living underwater in Antarctica also, where the temperatures on the surfaces are like really really cold for a lot of animals and plants to survive, right? But aquatic plants and aquatic life is still available even under Antarctica, right? So that is something that I wanted to tell you guys. Okay. And that is the end of it. That's the phenomena that I wanted to express. Okay, that is the anomalous behavior of water at 4 degree. For some weird reason, at 4 degrees the density is like the highest. Okay. Now I need you to understand one more concept here, a newer concept, and that is known as specific heat capacity. Do you know what heat capacity is? Tell me what heat capacity is, guys. What do you know from heat capacity?
The heat capacity would be like the amount of heat energy required to raise the temperature of a particular substance.
Okay, cool, awesome, that's perfect. Okay, so that's the definition. And the definition goes like this: the amount of heat required to change the temperature of a body by 1 degree centigrade is known as the heat capacity. That's definition. Everybody should remember it, right? But do you understand what heat capacity is? Like, for example, if I give you a simulation, okay, if I give you a simulation, like for example, 1 second, I have an experiment. Let's say I have an experiment. Where did it go? Yeah, let's say this is the experiment. Okay. uh Let me make it a little bit smaller. Okay. I need you to look at the experiment. So you see ki in the two beakers, there's like two things. One is water on the left hand side, on the right hand side, you have sand. And as you provide the same amount of heat, the sand is heating up really, really fast compared to water. Like same amount of heat on the bottom of both of these. And you see that the temperature of sand is rising much faster, right? So this is where the understanding lies. Okay, you know the definition, but can you tell me which of these have higher heat capacities?
So water.
Yes, that is absolutely true. Okay. So heat capacity, the understanding behind heat capacity is that it's the capacity to withstand heat, if that makes sense. So if you're providing or you're if you're burning a fuel and you're providing heat capacity, or you're providing heat energy to a system, and the temperature is kind of rising really, really fast, then it does not have too much heat capacity, right? The heat capacity for that body will be low because its capacity to take heat is less, right? So a body whose temperature sort of increases really, really fast or very easily will have lower heat capacities. In this case, water will have higher heat capacity than sand. So everybody, I think everybody understood this, right? So I'll write down the definition here. This is the official and the technical definition, but don't run after only the definition. You got to understand what they mean. It is the amount of heat. It is the amount of heat required. Excuse my handwriting today. Yesterday, I actually, yesterday I was riding my bike, not bike, I was riding like a scooty. I was driving it really fast, and uh, unfortunately or fortunately, I fell. I fell on the road. There was too much sand on the road. I was taking a turn, and I hurt myself on my hands. So there's a lot of scraping going on, but I think I'm able to write, but my handwriting is like shit. So is the amount of heat required to change by 1 degree centigrade? Okay. This is the official definition for heat capacity. Is the amount of heat required to change the temperature of body by 1 degree centigrade. Okay. So this is known as heat capacity. And I have another example here, another simulation, another beautiful simulation to represent this. This kind of makes, like, if you see this GIF, this one single GIF is able to explain what I was explaining for a while now, right? So you can see there are two bodies. One has low heat capacity on the left, the other one has like high heat capacity. You can see when same amount of heat is applied, you will see something that has lower heat capacity will rise in temperature really, really fast compared to something that has high heat capacity. Okay, so that is something that I wanted to share with you guys. That's heat capacity. Once you specify the quantity of the object, then you can specialize your heat capacity into two segments, right? Like if you take this same definition, I want to take this definition right here, which I had written here, is the amount of heat required. So I'll take this definition with me to the next slide, and I'll tell you how I can quantify this. So I'll make it a little bit smaller here, and I want to paste this. Okay. Right. So this is the definition for heat capacity. Okay, but I'm going to change it a little. It is the amount of heat required to change the temperature of, instead of body, if I say if the temperature of, instead of a body, I just say ki instead the temperature of 1 kg of substance, 1 kg of substance, then this becomes the definition for specific heat capacity. Specific heat capacity. Okay. So the only difference in the definition is I specified the quantity of the substance, right? So see the heat capacity for two different objects, for a sphere made of steel and a cylinder made of steel, would be different. Like if you have like 1 kg of iron and then 5 kg of iron, their heat capacities will be different. Obviously 5 kg ka heat capacity will be less because it's more mass. That means it will require more heat, right? But if you specify ki specific heat capacity is like for 1 kg of substance, then it kind of becomes like a material property, right? Material property means instead of saying 1 glass of water and then 1 tank of water will have like different heat capacities, but water itself, the material water itself will have a certain specific heat capacity, whether it is kept inside a tumbler or whether it's kept inside a truck, inside the ocean. Wherever water is, the water specific heat capacity will be same, right? But that doesn't mean ki if you have 1 glass of water and 1 full tank of water, they will take the same amount of heat to raise the temperature, because we are specifying ki I'm only doing for 1 kg. It becomes the material property rather than so the heat required will no longer be heat capacity. It will be mass into heat capacity into delta T. So this is the formula that you have to remember. I think you might have seen this in your chemistry. Okay. So Q becomes equals to ms delta T, where m is the mass, S is the specific heat capacity of the material, and delta T is the change in temperature. This you might have, again, if you have done through if you have completed thermodynamics in chemistry, and I don't know if you have you done thermodynamics in chemistry? Like how much have you done?
Yes, sir, we have finished thermodynamics.
Yeah, yes. So all of this might seem familiar to you. So I'm just detailing there. You just remember the formulas. I'm trying to detail here, like why you have something the way it is. Okay. So I'm trying to form the logic behind all of this. Okay. So the heat required to change the temperature of a body. Okay. That amount of heat that gets transferred onto a body is essentially mass multiplied by specific heat capacity of the material into the change in temperature, okay? So that is specific heat capacity. Now I'm going to do the same thing, but this time instead of 1 kg, I will say 1 mole of substance. Now, can you guess what we call this one?
So molar heat capacity.
Molar heat capacity. Okay. And the formula for that will be NC delta T, right? So this is, again, I think you might have seen this formula. This is the heat. This is number of moles. So again, the basic definition I have not changed. It's the amount of heat required to change the temperature by 1 degree centigrade. But one temperature of what? If you should just say a random body, then it becomes this heat capacity. If you specify the weight, specify the quantity in terms of weight, and you say 1 kg of substance, it is specific heat capacity, right? If you say it is for 1 mole of substance, then it becomes molar heat capacity, right? So this is like molar heat capacity, right? And delta T is change in, obviously it's change in temperature. Okay. So this is the idea here. This is the molar heat capacity. But one thing I need you to remember from your studies in thermodynamics is that in gases, whenever you do like a thermodynamic process, the kind of process you're following is sort of important. Like for example, if you do like isochoric, do you remember what isochoric is?
So the volume would be constant.
Yeah. Do you remember what isobaric is?
So pressure is constant in this process.
Do you remember the other processes?
So there's isothermal.
Adiabatic.
Yes, sir.
Right? So these are all the 4 processes. So what I was saying is that the heat capacity will also depend on the process, right? So molar heat capacity during an isochoric process is CV. It's like molar heat capacity when volume is constant, right? And isobaric process ke liye you say Cp, which is like heat capacity when you have pressure as constant during the process, right? So again, CpCv is not defined for solids and liquids. Mostly it's defined for gases, because for gases the process, the thermodynamic process that you are undertaking becomes kind of important. So if it's an isochoric process and you find out the heat capacity, the molar heat capacity, then it is known as, it is given by Cv, and then correspondingly Cp for constant pressure, right? So the process matters in cases of gases. So that's why you plug in these values. Anyway, anything else? Anything that you want me to explain or you didn't understand, please let me know. Right? We'll elaborate more on this when we reach the next chapter, which is thermodynamics, right? So after this, we'll doing thermodynamics. After thermodynamics, we'll do kinetic theory of gas. So in the next chapter, I'll be delving more into what Cp and Cv is. There's one Mayer's equation I hope everybody knows. Do you know what Cp minus Cv is?
It's universal gas constant R.
Yes. So this is another relationship. Just I need you to memorize for now, and I'll talk about where it came from and how it works. But just for now, I just need you to memorize it because you have already done that in your chemistry. So I'm not worried. You can just memorize this value for now, right? And we'll talk about where this Mayer relationships come from. I think you might have done it in chemistry. We'll do it. Nevertheless, we're going to do it uh, again in physics as well. But we will do it in a little bit different way. Okay, so the perspective is a little bit different. The concept is essentially the same. Okay. Now that you have understood what heat capacity is, let us move on to the next concept. Okay, so I'm talking about the next concept now. Okay. And anything regarding heat capacity that you want me to elaborate on, again, you didn't understand, I can explain. This is one another table that from NCRT that lists down all the specific heat capacities for the different bodies. So here you can see water का 4.186 joules per kg per Kelvin होता है specific heat capacity, right? Molar heat capacity is around 75 for water, right? And in terms of calorie, I think for water, the specific heat capacity is 1 calorie per gram. Okay, so that is something that you need to remember. Now,
So is it necessary that if a solid is a conductor, it should have a lower specific heat capacity?
I mean, conductor. If see the way we define conductor is that it has the ability to allow heat to flow through it very easily, right? So from that definition itself, it kind of makes sense कि something that has lesser resistance to heat, or in a way more uh, hmm. Okay, you can't directly say that, bro, because there is another quantity that we will come across. It's known as thermal conductivity, right? It's represented by K. That is the ultimate indicator of whether a body will be able to conduct heat or not. Okay. But as per my observations, I haven't seen situations jahan pe conductivity is more and specific heat capacity is less. So I don't have an exact answer for this, but what I'm trying to say here is that here you can see aluminum and copper, right? So copper being a better conductor of heat has lesser specific heat capacity, but I can't be sure of the trend, right? Aluminum and copper ka to I know, but I don't really know for other ones. Is lead a better conductor than copper? I'm not doing electricity. I'm talking about thermal. So what we will do is when we in the next class, when we are talking about the thermal conductivities, conductions, and all that stuff, there we'll get another figure like this where we'll have the conductivities for all the metals. Then we'll try to correlate between the specific heat capacity and the conductivity. So and the ultimate question Rishi has raised here is that does increasing conductivity mean decreasing heat capacity? Is that a thing? Well, I haven't researched on it, or I haven't come across any particular general statements being made like that. But we can see that when we have the table for the conductivities as well, and we can compare, and we can come to a conclusion. I think there might be counterpoints. That's why we don't have a generalized statement. Otherwise, there would have been a generalized statement. Okay. So yeah, about the next topic. So this is the table. So I'm not gonna ask you to memorize all of this. No, it's not required. Even if it is in the question, then they will provide the values to you in the actual exams, right? But water is something that if you keep on using, because almost a lot of questions from this particular concept will be about around water, right? So water ka use kar you will remember that its specific heat capacity is like 4186. Okay, so that's something to keep in mind for now. Now, anyway, let's move ahead to the next concept that I had promised, which is calorimetry. This is the last and the most important concept in this first segment of thermal properties. We have one more lecture where we talk about the heat transfers, which is tomorrow. Not tomorrow, I mean like next Sunday. What exactly is calorimetry? Okay, if I had to just simplify it to the best possible way to simplify this would be to say that whatever heat gained during a process, that heat is equals to the heat lost by a different body. What does it mean? Like, for example, if you have a bucket full of water, like you fill like some amount of water, x amount of water, which is at 30 degrees centigrade, right? Now, it's like cold water. 30 degrees centigrade is like generally a little bit cold. And you want to heat the water, so you have a jar full of I don't know, hot water, okay? And you throw in y amount of water whose temperature is, I don't know, 100 degrees centigrade, right? So you put a little bit of hot water onto a bucket of cold water. So what is the resultant temperature? Like, what will be the temperature of the water when mixed together? Will it be 100 plus 30 by 2?
So I think it will be dependent on the total internal energy or heat energy.
Yes. You got to understand ki, let's say, how do you approach this question is very, very simple. You say ki, okay, let's say the temperature see, obviously one thing that all of us will agree on, whether we know how to solve this or not, is that the equilibrium temperature when both the water when water is like completely mixed with one another will be somewhere between 100 and 30, right? That much too we can expect. There's no way that after mixing them together they become like 120 degrees centigrade. That's not like logically and experimentally you have never seen कि अगर मान लो तुमने 100 degrees का water 30 degrees पे put कर दिया तो 120 degrees का हो गया, right? Or maybe if you do 100 degrees and 30 degrees together, suddenly both of the water became 30 degrees centigrade. So that's like that violates the kind of conservation of energy concepts, right? So what I need you to understand is that if you mix 130, the first statement that you can make is the equilibrium temperature will be somewhere between 30 and 100, right? Now, when the water got mixed together, two things happened. The X amount of water which was in the bucket, its temperature increased from 30 to T. In the same time, the water which came from the jar lost its temperature from 100 to T. I hope that makes sense, right? So can you tell me, if there is an increase in temperature, the body had gained some heat? Yes, it gained some heat. Where did that heat come from? That's my question to you. Where did that heat come from? Yes.
So from
Where did
hot
this
water.
heat? Yes. When the hot water's temperature decreased from 100 to T, this Y amount of water lost some heat. They lost some heat. And what I'm saying is that calorimetry is just equating this gain heat to the heat loss. So heat gain is equals to heat loss forms the fundamental basis of any calorimetry based problem. Okay. Now, without further ado, uh, let us do like a simple question based on this. Let me see if I can find one. Okay. 1 second. Okay. All the questions seems to be what is this? All of them are from thermal expansions only. Ay. Ah. Okay, never mind. I'll teach you one more concept and I'll give a combined question. So I found like a question, but it's like a combined question where you need to know what latent heat is. Okay. So I'll quickly talk about latent heat again. All of these things you might have already studied when you were doing this for chemistry. Can anyone tell me what is latent heat? No, nobody knows what latent heat is. Okay.
I think it's
Do you
like
know?
the
Yes.
so it would be the energy required to convert a particular substance from one state to another at
Yeah.
the suppose melting point or boiling point.
Yes, that's correct. Right. So we all know ki the body changes state. Like for example, water is solid at 0 degrees and as well as liquid. Like I mean, there's a transition that happens. So if you're trying to go to like -1 or 2 degrees centigrade, you'll have ice. But if +1 and 2 degrees centigrade, you have water. So there's freezing and melting happening at a certain temperature, and condensation and evaporation or vaporization happening at another temperature. And then there's also some quantities, not water, but who can directly go from solid to gas or gas to solid. So the processes are known as sublimation and desublimations, respectively. Okay. Now, if I do an experiment, okay, and what is this experiment? I have a beaker full of water and I start heating it. Okay, so the temperature keeps on rising from 27 to 30 to 40 to 50 and so on, 80, 90, 100, right? But as soon as reaches 100, the water starts boiling. The water starts boiling. Okay, the water starts boiling. And no matter how much heat you provide from the bottom, the temperature of water is not going to increase. It keeps on boiling, but its temperature remains at 100 degrees. So what is happening to the heat that I'm providing from the bottom? If it's not raising the temperature, where is this heat going? Well, the answer is to change in changing the state. Because when changing the state of a body, energy is required to change the to change the state of the body from ice to water or water to vapor, right? So here, this is what I'm trying to make here in terms of that graph. You can see in the x-axis, I have the heat energy. And the temperature on the on the y-axis. So as you can see, as the heat energy is increasing, the temperature is also increasing. But as soon as it hits 100 degrees, the temperature just remains constant no matter how much heat I'm providing. This heat, which is required to change the body's state from liquid to gas, is known as latent heat of vaporization. This is known as latent heat of vaporization. Okay. Please let me know if that makes sense. Okay. Now the formula for latent heat is pretty simple. Okay. and it is actually equals to, one second, let me get rid of all of this. And it is actually equals to Q is equals to mass times latent heat. So the formula looks very, very similar to specific heat capacity wala formula, ms delta T, right? But there is no delta T here, because you got to understand ki latent heat of evaporation mein there is no delta T. The temperature does not change. That's the whole point, right? So you're just doing mass into latent heat of I don't know, depending on what scenario you're talking about. If the water is boiling, then latent heat of vaporization. If it's freezing, then you say latent heat of fusion, right? So both of these processes remain will require energy temperature to be constant. Which, what I mean by that, if you also start decreasing the temperature of water, the water will keep on going down and down and down, but at the point it reaches 0 degrees centigrade, its temperature is no longer going down. Then what is happening to all the work done that I'm providing to the fridge? Well, uh as the process of freezing is continuing, all that expended heat is uh, changing the state of the body. Okay, it's not contributing to change in temperature. So till all the all the water is completely frozen over, the temperature of ice will never be below 0 degrees centigrade. It will remain at 0 degrees centigrade till all the water is converted into ice. And the reverse process is also true. If when melting process is going on, till all the ice melts, the temperature of that system will always be 0 degrees centigrade. Okay, so I hope that makes sense. So the formula again is Q is equal to ml, where m is the mass and L is the latent heat. So latent heat of vaporization. Okay, vaporization, or just latent heat to generalize this, people call it latent heat of transformation, right? Any kind of transformation, freezing, melting, boiling, condensation, sublimation, desublimation, all of them are combinedly known as latent heat of transformation, right? The unit for latent heat of transformation will be like joules per kg. It will be like joules per kg, right? So all you have to do is multiply with mass and you get the latent heat. Now I think you'll be able to do the questions.
So I have a doubt in that.
Yes, please go ahead.
So is enthalpy of fusion and latent heat of fusion the same, or is there any technical difference?
No, it's just naming patterns, right? Okay. So don't get confused with both the concept. The names might be different, but the concept, underlying concept remains the same. Okay. Now let's see if you can do a question that I'm going to give you. Okay, that I'm going to give. Let's see if you can do this. It's one of those. I'm starting again. You're noticing how I start with NCRT and I keep increasing my level. So this is an NCRT question. See if you can crack this. Take your time. There's no hurry. Anybody found out the answer to this question? Given you 3 minutes to solve this. Do you need a little bit more time?
Could you give a
Just
minute?
Yeah, sure. Take a minute. But yeah, please, everyone, try this. Again, this is a very easy concept to understand. And if you try a little bit, you'll be able to understand in class only. So you don't have to put additional effort. So please, ask me doubts. Tell me the pain points, and I can help you out with those. Like whichever portion you are unable to understand, I can explain it. So please let me know if you have any doubts.
Done, sir.
Done. Very nice. Can you let me know?
So I'll send it to you, sir.
Okay. Let us talk about how to do this question. Okay. Okay. So first of all, I need you to understand that there's like again two sets of water that we are working on with here. Okay. So pay attention when I explain this. Okay. So first is that I have a block of ice. I have a block of ice which is at 0 degrees centigrade, obviously, and its mass is like 0.15 kgs, right? Okay. It has to become what? 6.7 degrees centigrade water. Yes, but I don't think it will directly become water, right? Water at 6.7 degrees centigrade. First, it will become water at 0 degrees centigrade. 0.15 kg of water at 0 degrees centigrade. During this process, how much heat will be lost? Or how much heat will be required? My bad. How much heat will be required? Well, you'll be using the formula Q is equals to M into L, right? You'll use Q is equals to M into L. Why? Because temperature is not changing. It's only the state that is changing. So the heat that is required is mass times the latent heat, right? Now, when the water at like 0.15 kg of water at 0 degrees centigrade changes to water at 6.7 degrees centigrade, 0.15 kgs, how much is the heat that is required? Can you tell me this time? How much is the heat required? Well, you'll be saying Q is equals to ms delta T. Q is equals to ms delta T. How do you find out this value? Well, mass is I'm calculating that value, okay? And this value is mass is 0.15. Specific heat capacity of water is how much? It is given in the question, 4186. And how much is the change in temperature, guys? Well, 6.7 degrees centigrade minus 0 degrees centigrade. So how much is this? I'm going to put this in a calculator. Rishi, how much did you get here?
So I got this one as 4.2 kilojoules.
Okay, let's quickly check this. Okay, so 0.15 into 4186 into 6.7. So it's like 12.6 kilojoules. Did you say 12.6 kilojoules?
I got it as 4.2, so I think might have made some error.
Or maybe I have messed up here. Once again, 0.15 into 4186 into 6.7. Oh, sorry. Yeah, it is 4.206. So it's like 4206 joules, right? This is what you got?
Yes, sir.
Okay. Right. Now you have another scenario. You're saying ki I already had water. There was this 0.3 kgs of water, which was at 50 degrees centigrade, which is now coming to a lower temperature, which is like 6.7 degrees centigrade. And with some weight is still 0.3 kg. Okay, now the question is, see, during this process of ice melting into water and then water rising in temperature, a lot of heat will be required. Who will give this heat? Like the total heat required will be how much? It will be ml plus 4206. Like this entire process made, this is the amount of heat that is required. Who is going to provide this heat, guys? Kaun dega heat? Well,
The cooling
see,
water.
the water which is going from 50 degrees to 6.7 degrees is going to lose heat, right? When you do Q is equals to ms delta T, this is the heat that is lost by water when the water reduced its temperature from 50 degrees to 6.7 degrees, right? And how do you find out that value? You're going to say, okay, sir, the weight is 0.3, mass is 0.3, S is still the same, so I think 4186. What is delta T this time? Well, 50 minus 6.7. 50 minus 6.7. So let's plug this in calculator one more time. Where's my calculator? Yes, this is it. Cancel. 0.3 into 4186 into. Can someone quickly tell me what is 50 minus 6.7? I think it's 43.3
Yes, sir.
into 43.3 is 54,376. So this comes out to be how much? 54 376 joules, right? So what will be the ultimate equation I write? I'm going to say something like this. Ki dekho 54,376 is equals to ml plus 4206. What is this equation? Where did I get this from? This is the fundamental basis of calorimetry that I posted here. I said heat gain is equals to heat lost, right? So in a closed system like this, whatever heat was expended by cooling the water will be needed in the ice. Actually, I think the color code is like ulta. The orange is generally like the heat provided, and blue is the one that comes out, right? So this is a cooling process, so this should have been like blue color, but it's okay. You understand this color code doesn't mean anything. I just chose random color and it's just the reverse of what it should have been. But anyway, if you solve this equation, children, I think you'll find out the value of latent heat, because again here M is also known. M is like 0.15, right? So if you solve this equation, your L will actually come out to be, and I'm giving you the answer from the NCERT itself. Latent heat of fusion comes out to be 3.34 into 10 to power 5. Okay. So I hope that makes sense.
So
3.34.
we don't take delta T as negative for the second case?
You can take negative, but the negative sign would it will tell you that the heat is lost during the process, right?
So we are basically focusing just on the magnitude of heat.
Yes. See, if you understand that this is the heat that is lost, then you can say that heat lost is equals to heat gain. Otherwise, if you just do it in terms of energy point of view and you get a minus sign, then you'll have to say that the overall energy of the systems remains the same. So you'll just say that energy 1 plus energy 2 plus energy 3 equals to 0. So whichever way you want to do it, you can do it. But I like to work with the magnitudes because it's not math. I know the meaning of the signs, right? So minus sign just indicates that your energy is going out of the out or heat is generated during this process, right? Heat is thrown out of the system, thrown out of the water drop, and it is utilized somewhere else. So I just basically like to work with the with the uh, y- with the magnitude.
Magnitude. Yes, sir.
Yeah, sorry. So this is the solution in that is given in your NCRT. This is actually a solved question. You can check this out in your NCRT. Latent heat of fusion is 3.34 into 10 to power 5. They have done the exact same way. You'll just get a little bit, don't get worried with this theta signs. Theta is the symbol for temperature. You might remember from units and dimensions, right? I don't like to use theta is because my Q's and thetas look very similar. So I am afraid I'll just cancel out heat with temperature. So I prefer to use capital T. It's up to you though. Both is fine. Okay. I have one more question. This too from NCRT, but it's a little bit tougher from what the one that we just did. Okay. So see if you can do this because I helped you with the previous one. I'm expecting a lot of you to be able to solve this one though, right? And after that, we'll do a few J mains question, and that will be the end of today's class as well. So go ahead, try this question. I'm making the question a little bit bigger. Yes. Anybody wants to tell me how to solve this?
So I got it how to solve it, but there's quite a lot of calculation. So I'm doing
You
it.
can use you can use the calculator for now. NCRT questions के लिए calculators are allowed. JEE mains के question के लिए do not use calculators because in NCRT they don't worry about whether the calculation is possible or not by hand. I'm saying, right? So as long as you're doing NCRT based question, you are free to use the calculator if you want. But if you're ever doing questions from modules or assignments, don't use calculator for any of those. But for NCRT के लिए, please remember you can use calculator. Everybody got how to solve this at least? I'm not talking about the calculations, but can someone put some light on it on how to do this? Kartik, what do you think? How we should proceed?
Sir, so first we can say that the 3 kg of ice from minus 12 degrees Celsius should then be converted to 3 kgs of ice at 0 degrees Celsius. That would become Q is ms delta T due to supplying of heat. Then that
Hmm.
ice would be changed to water, and that's
Mm-hmm.
where we can use Q is equal to ml.
Mm-hmm.
And from water to water at 100 degrees Celsius, so that's again
Mm-hmm.
ms delta T.
Mm-hmm.
And finally water at 100 degrees Celsius to steam using ml.
Very nice. Very nice. Everybody is comfortable with what he said. Um,
Yes, sir.
just want to know. I just want to know. Ishani, are you there? You're dropping from the you got dropped from the meeting.
Yes, sir. I
Okay.
just got disconnected. I joined back.
I understand. I understand. But did you understand how to do this problem? Can we like the calculation is not important, but Ishani, did you understand how to proceed in a question like this?
Yes, sir.
So how can you put some light on it? Like how should we proceed here?
So basically, first we try to calculate the heat required to convert ice from minus 12 degrees Celsius to 0 degrees Celsius. That is
Hmm.
ms delta ms del, ms delta T. And then
Yes.
similarly, heat required to melt ice at 0 degree to water. Then
Ah,
um, then heat from 0 degree to 100 degrees and from 100 degrees to steam.
awesome, awesome, awesome. Perfect. So I'll just quickly draw this. This is ice at minus 12 degrees centigrade. First convert ice to 0 degree centigrade wala ice. Okay, this is ice. This is ice. Okay. Then ice say you convert into 0 degrees of water, right? And then you'll have water goes to 100 degrees centigrade, water. Okay. And then you convert this into steam uh, that is at 100 degrees centigrade steam, right? So each of these will have different energies. So this one will have ms delta T, okay, and this one will be ml, this one will be ms delta T, and this will be ml. Okay, so m is same, but the specific heat of ice is kind of different. So I'll write SI here, okay, and this is SW. So all these terms will actually be different. So the first one will not do the entire calculation. It is okay. It is perfectly okay to not do the calculation, but you should at least do to the point jahan pe you are plugging in the values, right? So ice ka mass, everything mass is like 3 kgs, right? So the first formula will be 3 into what is the specific heat of ice? 2100, right? So 2100 into 12 because change in temperature is like 12. Okay, 12 degrees centigrade. Now the next thing is how much is the latent heat of fusion. So you will see mass is still 3 kg. Latent heat of fusion is this one, 3.35 into 10 to power 5. So this is the energy in the second one. What about the energy in the third one? Mass is still 3 kg. Specific heat of water is 4186. So I'll write 4186. Notice how I have used different formulas here, different values of specific heats here. And what is the change in temperature? Well, 100 degrees. Water is going from 0 to 100, right? So this is the third. And the last one will be 3 into latent heat of vaporization or latent heat of steam, which is 3 into 2.256. That is given in the question. This is the latent heat into 10 to power 6, right? So if you find out all of these and add them together, you get the final answer. You get the final answer on how much total heat will be required to change like ice to steam. Okay, so I think everybody understood the process. It was pretty easy after I had explained that one. And Karthik also actually has completely solved it. He's saying 9.1, which is correct. Okay. So your answer comes out to be 9.1 into 10 to power 6. So if you do all the calculations, you do get a 9.1 into 10 to power 6. Okay. So that's it for calorimetry from NCRT. Now let us see if I can I can give you some good questions from JEE Mains on calorimetry, right? Let's see if you can figure some questions out from from JEE Main level. So give me 2 seconds to find out a good question. Select a good question for you guys. Okay. Ooh. So I see a lot of question from thermal, right? But the very less questions are there from this particular segment. So let me search in the book. Maybe I when I selected those questions, I was preferential. Uh, what's this? Properties of matter. Remember, in JEE Mains, it's not going to be just one concept they're asking, right? So whenever they are going to give you questions, they're going to give you multi-concept questions where they will involve heat and solids and everything together. They will put. Okay, so that is something that you have to be very careful about. Okay, so let me see if I can find a good question from calorimetry. Okay, all the questions kind of involve thermodynamics as well in JEE Main. So I don't think we can find some just pure questions on calorimetry is not there. Each of these questions that I'm finding from JEE Mains is also mixed with a little bit of thermo, right? So I'll give you a module question in that. Yeah, that's my only option left. Okay. So I want to tell you about some questions in your module that you'll find like this. Okay. Read the question and let me know if you understand. This is from your module, by the way. These questions are from module. And if you don't know what concept is behind them, you'll not be able to solve it. Okay. Uh, let me tell you what they are talking about. Okay. Have you read the question? Read the question, please. 2 minutes to read the question. I don't think you'll find proper PYQs for this chapter alone. That's because whenever questions from this is asked, it will be mixed with thermodynamics, right? So no pure questions from calorimetry are there. It is mixed with thermo questions. So stick to modules for now. And after thermodynamics is done, then you'll find a lot of questions that you can do. Yes, guys. Okay, so now guys understand what they're talking about. Okay, now what happens is, for example, I give you a container. Okay, I give you a container which is filled completely with water. Let's say this is a glass container, the glass container whose volume is, let's say, 1 liter. Okay, and you fill it completely with, you fill it completely with water. Okay, let's say this is right now at the room temperature. Now you increase the temperature by T degrees centigrade. Okay, for both the glass as well as water, right? The glass will expand according to its coefficient of expansion, and water will also expand according to its uh, expansion coefficient. Okay, now the question is, will will the level of water, will water spill off, or will the water level remain at top? What exactly will happen? Well, it will depend on the value of alpha W and alpha G, right? Now what happens is alpha W is actually greater than alpha G. What I'm saying is that coefficient of thermal expansion is of water is more than glass. So that means water will expand more than glass. So when you raise the temperature of this entire system by, let's say, 100 degrees centigrade or something, the volume of water will also increase, but the volume of glass will also increase. But the volume of water that increased will be more compared to the volume of glass. So what will happen, guys? Some of the water will be spilled out. Yes or no, guys? You have to figure out how much that spilled out water is. Okay, so in terms of variable, you have to do first do that question, and then we can do this in the next one. Okay, first do this question, do it in the variable form. If you're able to do this question, a lot of question in your in-text exercise will become simple for you, right? So let's say the volume given is also, let's say, a variable. Let's say the initial volume of glass and water, fully filled glass of water is V, right? Alpha for glass is given as alpha G, and alpha for water is given as, the linear expansion coefficients are given as alpha G and alpha W for water and glass. So as the temperature T is increased, tell me how much volume of water will be spilled when the temperature is increased by T degree centigrade. Guys, comfortable with the question?
So for water, it would be gamma, or why would it be alpha?
Dude, I have given you alpha. Gamma will be what? 3 times of alpha.
So, but in the question, did they mean that it was gamma or alpha?
See, in the question, they will never give you gamma, because of the relationship. Whenever they give you alpha, you by default all the quantities beta and gamma are known. These are, you got to understand, these quantities are not, these things that are happening, or the expansions that are happening, are not mutually exclusive. All the things are happening. There's linear expansion, there's area expansion, there's also volumetric expansion. Does that make sense? Right?
Yes, sir.
So so they will always check out all the questions in your module. They will never give you gamma or beta. They will always give you alpha. They will give you linear expansion only. It's up to you, depending on what you want. If you're talking about how much area of water, I mean, the cross-sectional area of water has increased by how much. In this case, it won't. But in certain scenarios, they will tell you, what if the volume, the area is increasing. Okay. how much will the area increase, or the height of the liquid, how much does the height of the liquid increase. So all of that scenarios you have to deal with depending on what kind of dimension you're dealing with, right? So if you're talking about area, then use 2 alpha. If you're talking about volume, then 3 alpha. If you're talking about one linear dimension, then alpha. Go ahead, do this question. Water spills out. Yes. How much, Karthik? That's the question.
In variable form only, how much?
Yes. In a variable form only, how much? Oh, ouch. Yes. Awesome. Karthik has answered. See, it's very, very simple, guys, if you think about it. What is the change in volume in water? Well, you're going to say V into 3 times of alpha water into T. What about the change in glass, volume of glass? Well, you're going to say V into 3 times of alpha glass into T. So what is the volume that's excess, which is going to spill off? Well, whatever is the extra. So for example, this increased by 200 ml, but the volume of glass increased only by 100 ml. So how much is the spill off? Like 200 minus 100, right? So you're going to do delta VW minus delta VG. So your answer will be V3VT bracket mein alpha W minus alpha G. Now, you will see a lot of module questions where this value is given to you. They will give you the spilled water is this much and find out the coefficient of glass, find out the coefficient of water, etc., etc., and they will give you the other values. You just plug it into this equation and you solve it. Okay. Now, this question that I had given you from the module, this was asked many times to my by my students. So I tend to take this in the class itself. Is what is coefficient of real expansion of liquid and what is the coefficient of linear expansion of what is the apparent expansion of liquid? Okay, it's the difference. See, usually real expansion is like, okay, the water has increased in volume by this much amount, right? A delta V, right? But if the container in which you are measuring the liquid also increases in size, then the new delta V will be what? The apparent coefficient of expansion. Okay, so this is something that I wanted to tell you, is that like for example, in the first case they have told us that alpha of liquid is given to us as what? 0.00182, 0.000, sorry, 0.0000182 per degree centigrade, right? And alpha of glass is 0. How many zeros is this? 5 zeros? 1, 2, 3, 4, 5 zeros per degree Celsius, right? Now, if you have a container जिसका जिस पे दोनों पे you have like the same amount of volume, then the expansion of liquid let's say it doesn't have to be filled this time. Okay, so I'll make it a little bit bigger, otherwise again water will spill, right? So you are measuring the volume of a certain liquid using this measuring cylinder, okay, and it comes out to be V. Okay, now what happened is the change in volume of the liquid is going to be what 3 times of alpha L into whatever the temperature is into this original volume, right? And the change in volume of the glass up to this level will actually be 3 times of alpha glass into temperature into volume, right? So what is the actual increase in volume of liquid compared to like the new container? It will be the difference of the two, right? The same concept. Okay, so which will be like TV 3 times of 3V alpha L minus alpha G. Okay, now apparent is like you're seeing only the liquid increase in and you're trying to figure out ki how much is the delta V by V for liquid from the new perspective, which is like this delta V L dash, I should say delta V L dash, which is like the actual increase with respect to the new container. Okay, new container which is already expanded, right? So delta VL dash divided by V would be like 3T into alpha L minus alpha G. Okay, so that means it will be 3 times of how much is 182 minus how much is 1 2 3 4 5. So this is like 182 minus 1 2 1 2 3 4 5. This is 1 2 3 4 5. So okay, 182 minus 9. What is
173.
173?
173.
Yes, 0.000173. Okay, so that will be how much? Yeah, so I don't even need to do any further. So this is what you see, right? The delta VL dash by delta V is 3 times of this value. So when a normal person who doesn't know that the volume of container is also increasing, he's going to see that okay, the new volume has increased with a rate of 0.00173, because he's not knowing that the container is also increasing in size. This is known as coefficient of apparent expansion of liquid, because he's not taking into account that this is actually happening because of glass also increasing. The actual alpha of the liquid is 0.00182, but because the glass is also expanding with it, the rate at which the liquid is expanding with respect to the expanding container is slightly less, right? I hope that makes sense. So this particular number is known as coefficient of apparent expansion of liquid. So the answer to this question would be like C option. Did everyone get it? Please let me know if you understood this.
Sir, so apparent expansion is when he does not consider the increasing volume of the container.
Yes, yes. Do you this apparent thing also came in optics? Do you know what apparent depth is?
Sir, like when you see it at a specific angle, it looks like at a higher level
You
than.
might have you might have done this in your
And refractions.
in your refractions of nine standards. Whenever water is involved, what happens is, let's say if you're watching the if the body is at the bottom of the like there's a coin at the bottom of this is the real depth. This is known as the real depth, right? But if you watch from an angle, what happens, the ray that is coming from the liquid kind of refracts. You know, okay, whenever light is going from a denser medium to a rarer medium, it bends away from the normal, right? So the ray kind of bends, but our eyes are not able to perceive this. Our eyes will see ki okay, the ray is actually coming from here, so maybe the coin is located just right here. So this we call apparent depth, because this is where our eyes will perceive the object to be, because we don't know our eyes will not be able to perceive this ray coming from at an angle like this, right? So that's why whenever something is kept at the bottom of a tumbler, it appears a little bit elevated. Same reason the pools, the swimming pools appear a little bit of shallow. This is known as apparent depth. Same concept here also, right? The same fundamental reason. The container is also expanding with the liquid, right? So the actual expansion of the liquid is actually more, but because the container is also expanding with the liquid, the apparent expansion that we are seeing is actually slightly less. I hope that makes sense. Okay, so this is one of the questions that I wanted to check from the module. Okay, let us end today's class. If you have any doubt regarding any of the concepts, please ask. Do not leave though. I'll quickly have to take the attendance. 1 second. I forgot to take the attendance. I think Shrishti left, so I want to mark her attendance. She might have been dropped. Anyway, thank you for being here. If you have any doubts regarding anything that we have studied till now, please ask. Next class, we are starting the heat transfer. Same chapter. And regarding the recordings, Karthik, I think you were asking me the recording for previous class. So one of the files got kind of corrupted. So I don't know what to do. There is an equivalent lecture that Dheeraj sir has taken. It is available in the JEE physics. So you have access to Learnist, right, Karthik?
Yes, sir. And you also sent the link for all the recordings that you had sent before.
So what happened is one of the recordings, I don't know what happened in YouTube. So uh, my team, they extracted it from Zoom and then they uploaded it, but there was some error and the original file got deleted after some time. So that's why I don't have like the second lecture. This is my first time recording all my lectures. So uh, occasionally I'll have some lectures missing. So what you can do is same lecture that I give is also in the recorded form, but it's taken by Dheeraj sir. So he's my he's physics HOD. So he's equally capable, if not more. So you can go to the JEE physics section, and there under every chapter you'll have like 3 lectures. So I'm following the exact same. We have the exact same POW. So we teach the exact same stuff. So you can watch that recording as well. If you miss any class, you can and you can also watch a little bit of ahead also. Like if you know you're gonna miss the class on next Sunday, why not watch the video relevant to that in a week ahead of time. Okay, that way you can ask doubts, better doubts. Okay, so if you know you're missing if you're going to miss the class, just watch the corresponding recording from Learnist. All the lectures that I have taken are there on the Learnist itself, the platform through which I give the assignments. Okay, and yeah, that should be it. But anyway, please let me know if you have any other doubts.
Yes, sir. I'll watch the recordings from Learnist, sir. Thank you.
Uh-huh. Any other doubts, guys? Please ask.
So you told me that there's a problem solving video which you had done on fluids. So if
Oh,
you
yeah.
could send that link on the group, it would be helpful.
Okay, I'll send it. I'll send it now only so that I don't forget. Where is that recording? I'll download and I'll have to download it, or I'll send a link to you personally. See if you can open it. If you can open it, then I don't have to download it and upload it on YouTube or something. Let me see. Where is it? It's in 11th only. Okay. Kindly do the assignments, guys. It's kind of important. Okay, let's end this lecture. I have your number, Rishi, so I'll send you directly. If you can open it, just let me know through the message. If you can't, then I'll upload it on YouTube and then send link to everyone. Okay. Otherwise, I'll send that link directly to the group. Thank you guys for being here.
Thank you,
See you
sir.
next class.
Thank you,
Thank you,
sir.
sir.
Thank you.
Thank you, sir.